Section 1, Collision Theory, Knowledge and Communication. Collision theory explains how chemical reactions occur. For a reaction to be effective, it must meet two criteria. Sufficient energy. Particles must possess the minimum kinetic energy, known as activation energy, to break existing bonds. This energy is needed to reach the activated complex, transition state. Correct orientation. Reactant particles must collide in a specific alignment to allow atoms to rearrange. Factors affecting reaction rates. Concentration. Increasing concentration increases the number of particles in a volume, leading to more frequent collisions. Temperature increases average kinetic energy, leading to more frequent collisions and a larger fraction of collisions having energy greater than or equal to the activation energy. Surface area exposes more reactant particles for collisions in a heterogeneous reactions. Catalyst speeds up a reaction without being consumed by providing an alternative pathway with a lower activation energy. Section 2, expressing and calculating rates. Application. Reaction rate is the change in concentration per unit time, so R equals C over T. For the general equation reaction, little a, big A plus little b, big B turns into little c, big C plus little d, big D. The rate is expressed as rate equals negative 1 over A times the change in A over change in time equals negative 1 over B times the change in B over the change in T plus equals positive 1 over C times change in C over change in T equals positive 1 over D times change in D over change in T. And for the change ones, those are the capital ones, and then for the little ones, those are the 1 over. And then prompt, so example, so in the reaction N2 plus 3H2 equals 2NH3, the rate of formation of NH3 is 4 moles L times S. Find the rate of N2 consumption. So given the rate, the mole ratio required is the rate of N2 consumption. So analyze rate of N2 equals rate of NH3 times the 1 mole of N2 over 2 moles of NH3. Solution rate equals 4 times 0.5, which is 2 moles over L times S. Statement, the ratio of nitrogen consumption is 2.0 moles over L times S. Rates law, so the rate law is rate equals K xm times yn, where K is the rate constant and M and N are the reaction orders determined experimentally. So determining orders from data tables, if concentration doubles and the rate does not change, then the reaction order is 0. If the concentration doubles and rate doubles, the reaction is first order. If concentration doubles and rate quadruples, the rate order is second. So unit for rate constant, K. First order overall is S to the power of -1. Second order overall is L over moles times S. Third order overall is L squared over mole squared times S. Section 4, potential energy diagrams. So these diagrams track energy changes over the reaction process axis. So exothermic products have lower energy than reactants. Change in H is negative, energy is released. Endothermic products have higher energy than reactants, H is positive, energy is absorbed. Activated complex, the peak of the energy barrier. Catalyzed pathway, shown as a dashed line with a lower peak, lower EA, activation energy, but starting and ending points, change in H, remain the same. Reaction mechanisms. Most reactions occur in multiple elementary steps. Intermediate, a species produced in one step and consumed in a later step. It is not the overall equation. Rate determining step, RDS, the slowest step in the sequence. The overall rate law matches the RDS reactants. Mechanism plausibility, that's also the slowest. The steps, not for mechanism plausibility, the steps must sum to the overall balanced equation, and the RDS must predict the observed rate law. The Advil and bathroom questions. So the Advil question, why do liquid gel caps work faster than solid tablets? Answer, the liquid gel cap has a higher surface area once the casing dissolves compared to a solid tablet, which must be broken down layer by layer. Most surface area more surface area equals more frequent collisions between medicine, and your body's enzymes equals faster relief. The bathroom question, why is it bad to store medicine in the bathroom? Answer, bathrooms have high humidity, moisture, and temperature fluctuations. Higher temperature increases the reaction rate of chemical decomposition, meaning the medicine expires or becomes inactive much faster than in a cool, dry place. 2, potential energy, the reverse calculation. So EA and change in H in reverse reaction. So the rule, if you flip the reaction, H reverse, just flip the sign. So if forward is negative 50 kJ, reverse is positive 50 kJ. And if activation energy is reversed, this is the distance from products to the peak. So calculation, so energy reversed equals energy forward minus the change in H. The enzyme substrate trap. So if you double the concentration of reactant substrate, but the rate stays the same, what is the order? It is zero order. In biology, this happens when the enzyme is saturated. All the workers are busy, so adding more work doesn't speed things up. Mechanism plausibility. A question will give you a mechanism and ask, is this plausible? You must check 2 things to get full marks. Add them up. Do the steps simplify to the overall balanced equation given in the prompt? The slow step, does the rate law derived from the slow step match the experimental rate law given in the question? Example, if the slow step is A plus B turns into C, the rate law must be rate equals K AX B Y. And then chemical kinetics and reaction mechanisms. So fundamental concepts, kinetic theory and reactivity. Kinetic theory relates the motion of particles to the temperature and energy of a system. Heat of reaction, the energy change associated with the chemical reaction. Transitional structure, transition state, a high energy unstable state that occurs during a chemical reaction when reactants are being converted into products. Factors affecting reactivity, lower activation energy results in increased reactivity. More electropositive typically leads to increased reactivity. Inhibitors, an inhibitor extends the shelf life of a packaged food by slowing or stopping the chemical processes that cause food to spoil. It creates an unfavorable environment for these reactions to occur. 2, reaction mechanisms, elementary process, a single fundamental step in a chemical reaction mechanism where reactants directly convert to products via a singular molecular collision or rearrangement. Rate determining step, RDS, the slowest elementary step in a multi-step chemical reaction mechanism. It dictates the overall reaction rate. The rate law for a chemical reaction is determined by the slowest step in its reaction mechanism. Term molecular collisions, collisions involving 3 or more molecules. These do not typically represent the reaction mechanism as they are statistically improbable. Determining the overall reaction from elementary steps. Procedure, add the equations. Sum all reactants on one side and all products on the other from each step. Identify intermediates. Look for species that are produced in an early step but consumed in a later step. Appears on the right side, other things that are intermediates. Appears on the right side product, then on the left side reactant in a subsequent step. Does not appear in an overall balanced equation. Mostly highly reactive and short-lived. Note, intermediates are created during the reaction and were not present at the start. Cancel intermediates. Eliminate these species from both sides of the overall equation. Cancel catalysts, if any. Look for species present in an early step and regenerated later. Write net equation. Combine the remaining reactants and products. So example, identifying intermediates. So A plus B turns into X, fast, X is produced. Step 2, X plus C turns into D, slow, X is consumed. Identifying the rate determining step. Given the overall reaction, elementary processes, and the rate equation, follow these steps. 1, match reactants to rate equation. Look at the reactants in the given rate equation. Find the elementary step where the reactants, including coefficients, produce that exact rate law. For elementary steps, the coefficients of reactants are their orders in the rate law. Find the slow step. Identify the slowest elementary step. The step marked slow is the RDS. Verify. Reactants of the chosen slow step must be part of the overall reaction or formed by a previous fast equilibrium step. If the slow step is the first step, the rate of law of that step is the overall rate law. Important note, if the rate law shows a reactant with a coefficient of 2, The slow step likely involves two of those molecules colliding. E.g., if rate equals k times a times b, look for a step with a plus b turns into blah, blah, blah. Solving kinetic problems involving subsequential steps. So slowest step rules, overall process speed is defined by the slowest step. Bottleneck analogy, similar to chemistry, the slowest elementary step in a mechanism dictates the rate. Efficiency, adding resources like extra students or catalysts only improves productivity if applied to the bottleneck step. Complexity, increased complexity, more detailed steps, decreases the rate of a specific step and consequently the total process rate acts like a higher activation energy step. Quantitative calculations, example, energy calculation, total energy release, 100.3 kilojoules for 2 moles of NH3. Heat release per mole of NH3 is negative 100.3 over 2 moles, which equals negative 50.15 kilojoules per mole. Steps to calculate required mass. First, balance the chemical equation. Second, convert the given amount, energy or mass, to moles using N equals M over capital M. 3, apply mole ratio. Use coefficients from the balance equation to calculate the moles of reactants needed. Example, 1 mole A over 2 mole B. 4, convert moles to mass using M equals N times capital M. Multiply moles by molar mass.